To build a global proximity service, like Yelp, Uber, or Tinder, you have to solve one specific engineering problem: searching physical space at massive scale with near-zero latency. The most intuitive way to build this is to store every business with its latitude and longitude coordinates. When a user opens the app, you draw a bounding box around their location and run a simple SQL between query to find everything inside that box. To speed this up, you would naturally add a database index to those coordinate columns. But standard B-tree database indexes are designed to optimize one-dimensional data. They sort single values sequentially. Because latitude and longitude are independent dimensions, the database must separately fetch locations matching the latitude range and those matching the longitude range. It then loads both massive datasets into memory to perform an intersect operation and find the overlap. This architecture runs flawlessly when you're querying a sterile test environment with 50 dummy locations. But deploy it to a densely populated grid like downtown Tokyo, and the database grinds to a halt under the memory overhead of massive intersections. Databases excel at searching single, flat indexes. To search spatial data efficiently, we have to find a way to take a two-dimensional map and mathematically crush it down into a single one-dimensional string. The industry standard for solving this is an algorithm called Geohash. It starts by taking the entire globe and slicing it in half at the equator, and then in half again at the prime meridian. Each of these 4 quadrants is assigned a binary value. The algorithm then recursively divides each grid into 4 smaller grids, appending a new binary digit each time. Once the grids reach your target size, the binary sequence resolves into a short, base 32 alphanumeric string. This encoding creates a strict precision rule. The longer the alphanumeric prefix, the tighter and more precise the geographic grid it represents. But this grid system creates a severe edge case known as the boundary issue. Because the initial cuts divided the globe along fixed meridians and equators, 2 locations can be sitting right next to each other physically, but end up on opposite sides of a major grid division. This map shows La Roche-Chalais and Pomerol in France. They are only 30 kilometers apart. But because they sit on opposite sides of the prime meridian, their geohashes, U00 and EZZZ, share absolutely no prefix. If a user is standing near a boundary, a standard prefix search will completely miss the businesses right across the street. The software solution is to have the application server calculate the geohashes of the 8 neighboring grids in constant time, and query the database for all 9 areas simultaneously. This string-based approach makes dynamic searches highly efficient. If a user expands their search radius, the system doesn't need to compute complex geometry. It simply drops the last character from the geohash string, instantly zooming the query out to the larger parent quadrant. Geohash is mathematically elegant and requires no state to be maintained on the server. However, it imposes a rigid, uniform grid over a chaotic world, making it completely blind to actual human population density. Because Geohash uses fixed grid sizes, it allocates the exact same indexing resources to a massive empty square in the middle of the Pacific Ocean as it does to the densest blocks of Manhattan. This leads to highly uneven data distribution across your servers. To adapt to population density, use a quadtree. It recursively subdivides a grid into 4 smaller quadrants only if it contains more than 100 businesses. Unlike Geohash, a quadtree is an actual in-memory data structure. The server builds this hierarchical tree at startup, connecting the entire globe at the root, down to the heavily populated leaf nodes. This map of Denver shows the real-world execution of this logic. Around the major city center, the grids subdivide into tight, highly granular blocks, while the empty plains to the east remain as massive, low-resolution quadrants. Tech giants like Google and Tinder optimize this even further using Google S2, which maps a sphere to a 1D index using space-filling Hilbert curves. That is the elite standard, but mapping curved 3D space is generally overkill for a standard system design interview. The real operational penalty with a quadtree comes during write operations. If a business opens or closes, the system must traverse the tree in O log n time to update the node. Because this is an in-memory structure serving concurrent requests, you have to implement thread locking. If a leaf node hits capacity, the system has to halt and rebalance the tree.
A quadtree flawlessly optimizes read paths by perfectly balancing data density, but the complex multi-threading logic it requires for writes means that for most standard architectures, Geohash remains the safer, more resilient baseline choice. With the geographic math solved, the system must now physically store and serve data for hundreds of millions of global businesses. The primary database table holding the actual business profiles, names, addresses, photos, and review data will be massive. To handle this volume, this table must be horizontally partitioned, or sharded, across multiple database servers. By hashing the business ID to assign the shard, we guarantee that the massive storage requirements and write operations are spread evenly across the entire cluster. Instead of introducing complex application layer sharding logic, the correct move is to keep the index whole and duplicate it across multiple read replicas to handle the query volume. Adding the operational overhead of database sharding to a dataset small enough to fit in a smartwatch is a complete waste of resources. To drive latency down to single milliseconds, we need a caching layer in front of the database. The intuitive approach is to use the user's exact latitude and longitude as the cache key, but mobile GPS coordinates fluctuate constantly. Even if a user stands perfectly still, their reported coordinates will drift by fractions of a degree. Using exact coordinates means nearly every request is treated as unique, driving your cache hit rate to 0. The solution is to use the computed geohash string as the cache key. Because a geohash represents a defined, static area, it effortlessly absorbs those micro-movements, allowing thousands of users in the same block to hit the exact same cached data. We deploy a dual-tier Redis architecture. The first cache layer maps the geohash string to an array of business IDs within that grid. The application then takes those IDs and hits the second cache layer, which returns the fully hydrated JSON profiles for those specific businesses. By decoupling the spatial index from the business data, the system can serve detailed location results instantly from memory, bypassing the heavy database cluster almost entirely for read operations. To serve a global user base, these stateless location-based servers and their connected read replicas must be deployed across multiple geographic availability zones, physically positioning the computing power as close to the end user as possible. This regional isolation provides a critical secondary benefit. By ensuring European users connect strictly to European data centers, the architecture natively complies with local data privacy laws like GDPR and CCPA. This is how a modern proximity service scales. A mobile request hits the load balancer, a stateless server calculates the surrounding geohashes, hits a two-tier Redis cluster for the raw profiles, and returns a rich, sorted map to the user. It is an immensely complex two-dimensional spatial problem, solved entirely by routing internet traffic through a simple one-dimensional string.